Earth's climate is a puzzle. Over the eons, it has changed many times. As surely as the seasons come and go, warm tropical periods have exchanged places with epochs that encased much of our world in ice. By searching among Earth's simple rocks, deep in the ice of the frigid Antarctic, and far beneath the sea, scientists can now decipher some of the tales of our planet's many climates. Now they are also gaining a vision of the future. Here in Colorado, scientists use an electronic crystal ball to see well beyond our lifetime. The image that emerges is dramatic and disturbing and raises even more questions about the perplexing climate puzzle of planet Earth. Although the advance and retreat of ice seems inevitable, Earth's climate has remained surprisingly temperate over billions of years. Now scientists have uncovered another paradox. It appears our ancient sun was once smaller and radiated less heat than it does today. If the sun was faint, snow would gradually accumulate and the planet grow colder and colder. Eventually, the oceans would freeze, and Earth would become a glistening planet of ice. But there is no such evidence for this scenario. Liquid water, the basis of life, has existed on Earth for nearly all of its history. A clue to the mystery can be found millions of miles from planet Earth. When the first probes ventured to Venus and Mars, they discovered atmospheres fierce and alien to our own. Venus is hot and noxious. Nearly 900 degrees Fahrenheit at its surface, its rocks glow red. This hothouse climate exists because the thick acid clouds contain an extraordinary amount of carbon dioxide. Glass of a greenhouse, carbon dioxide traps heat and prevents it from escaping back into space. The atmosphere of Venus contains some 300,000 times more carbon dioxide than planet Earth. If long ago Venus had liquid water, it boiled away into the atmosphere of this hellish world. At the opposite extreme is Mars, a frozen planet. A land of massive volcanoes, its landscape is testimony to the violent activity that once may have pumped enough carbon dioxide into its atmosphere to warm the planet. The scoured surface of Mars suggests it was once warm enough for liquid water to forge deep canyons and river valleys and to carve great floodplains. But somehow Mars lost its ancient atmosphere, its liquid water disappeared, and what remains is a frozen, decimated world. In orbit between Venus and Mars is Earth, neither too hot nor too cold. It has an atmosphere with just the right amount of carbon dioxide for life to flourish. Unlike Venus and Mars, the Earth's surface is constantly changing, scoured by wind and water and torn apart by powerful forces within. The carbon stored in the Earth is continually recycled through the land, the oceans, and the atmosphere. Even life plays an important role in the cycle. This dynamic process helps control the amount of carbon dioxide in Earth's atmosphere and seems to resolve the mystery of our ancient sun. If there was more carbon dioxide in our early atmosphere, it could have trapped enough heat to keep the planet warm. Scientists now believe that abrupt changes in carbon dioxide can cause abrupt shifts in climate, perhaps even influence ice ages. And like Venus and Mars, create radically different worlds. This understanding of the role of carbon dioxide is among the great insights of modern science. Now there is a new urgency to understand the role of carbon dioxide in the life of the planet Earth. Since the advent of civilization, and particularly in the industrial age, man has injected enormous amounts of carbon dioxide into the atmosphere by the burning of coal, oil, and gas. The techniques of slash and burn deforestation to create fields for farming releases still more carbon dioxide. A time bomb seems to be ticking in our atmosphere. The climate of Earth is maintained only when the amount of solar energy absorbed by the planet equals the amount returned to space. As carbon dioxide increases, it retards the escape of energy. Like a greenhouse, Earth's lower atmosphere heats up. Hawaii's Mauna Loa Observatory is an ideal laboratory for sampling the Earth's atmosphere. Here in 1958, Charles Keeling of the Scripps Institution of Oceanography developed a method for measuring carbon dioxide. Since then, carbon dioxide has risen some 9%. At this rate, it could double sometime in the next century and raise the mean temperature of Earth some 3 to 10 degrees Fahrenheit. Such global warming could lead to the most dramatic change in Earth's climate since the last ice age, a change far greater than any experienced by mankind. The predictions of warming are fiercely debated, but all agree we are performing a great experiment on ourselves and our planet. The results of a potential carbon dioxide warming may eventually be seen here. Since the International Geophysical Year in 1958, Antarctica has become a natural laboratory where the dynamics of ice are explored by scientists from around the world. Here, global warming would create a special threat. Most of the Antarctic continent is covered by ice nearly 2 miles thick. Much of it rests not on land, but in the ocean. It is unstable and susceptible to movement. Scientists are concerned. Could Antarctica lose its ice? They explore even the slightest change in the vast and complex ice cap. They map crevasse fields, great frozen rivers that slowly but steadily flow into the Ross Ice Shelf, a floating slab of ice the size of France. The Ross Ice Shelf acts as a plug. It holds back the huge mass of ice that covers West Antarctica. Warming could cause the shelf's leading edge to disintegrate and destroy the barrier that contains the unstable West Antarctic ice sheet behind it. If West Antarctica's ice sheet collapses and melts, sea level could steadily rise some 20 feet to dramatically change the geography of planet Earth. Venice, the crown jewel of the Adriatic. Latticed by canals that form its streets, Venice is often flooded by storms at high tide. If carbon dioxide were to substantially warm the Earth, such flooding could become commonplace. Even a small increase in sea level could cause havoc. Storm surges at unusually high tide would threaten coastlines more and more frequently. Eventually, cities would have to respond with dikes and barriers, like London has now installed across the Thames to protect it from tidal surges that threaten even now. But populous countries built on coastal plains just above sea level are most vulnerable. In 1970, 300,000 people died during a ravaging storm surge in Bangladesh. A warmer climate could change growing seasons and make temperate regions much drier. The breadbaskets of the world might shift. The Soviet Union could replace the American Midwest as the world's leading producer of grain. In countries dependent on irrigation, the warming could be devastating. Hotter, drier climates could put still greater pressures on now arid regions. Desert areas would expand. Those who depend on the world's rivers for water may well experience hardship. The Colorado River, which delivers water to America's desert states, already loses more than 3/4 of its supply to evaporation. Rising carbon dioxide would also act as a global fertilizer for green plants that thrive on it. Explosive growth could radically alter ecological balances that have evolved over billions of years. We know that climate shapes life. We can only guess at the impact on life from a rapid and major change in global climate. Still, there is a great uncertainty about the consequences of a global warming. Some undoubtedly would benefit, others would suffer. The consequences of a carbon dioxide warming are serious enough to be considered the most important challenge in modern climate research. At the National Center for Atmospheric Research in Boulder, Colorado, meteorologist Warren Washington designs experiments called climate models that simulate the atmosphere of Earth.
This is one of the world's fastest computers. It is able to do 100 million operations per second. We're able to do things that we couldn't do 10 years ago on the computer. For example, we're able to generate a computer model of the atmosphere that simulates the winds, the temperatures, the pressures, the rainfall, the snow cover over 23,000 points over the entire globe.
Simulating the dynamics of Earth's atmosphere is a complex task. The land, oceans, polar ice, even life can influence climate. External factors like changes in radiation from the sun can further complicate the model. The enormous speed of the computer manipulates the many climate factors. The simulated Earth is turned on and run for a few computer days to predict weather, or for years to predict climate. By changing the factors of the climate model, the scientists in Boulder can perform tests that are not possible in the real world. They explore the scenarios that might reveal the causes of global climate change. Climatologist Steve Schneider uses models to explore the possible impacts of a carbon dioxide warming.
The question we have to ask ourselves is, what are models good for? Why do we need them for the future prediction of climate? Well, if we're going to try to figure out what's going to happen in the future, we need to estimate how much greenhouse gas humans are putting in, and then we have to ask what that's going to do to the climate. Well, if you haven't got a physical model, a twin Earth, if you will, that we can go and pollute by adding greenhouse gases to and then see what happens, the only other model we can build that has any plausible hope of telling us about the future is a mathematical model, which we build and run inside of a computer. We take this model and we describe the present climate in it, essentially simulate the present climate. We then add greenhouse gases that humans are adding to the model, ask the model how has the climate changed, compare the two, and have some idea of what the future might bring us climatically if we did that kind of addition of gases.
While some scientists speculate on the future of carbon dioxide in the atmosphere, others test an intriguing scenario of climate in the past. Today, this semi-arid region is part of Colorado's Pueblo Reservoir State Park. But when dinosaurs ruled the Earth, it was covered in water. Searching among the ancient rocks for evidence of the ancient sea is geologist Eric Barron.
These rocks date from the Cretaceous period, about 90 million years ago. The characteristics of these rocks and the fossils we find in these rocks tell us that this area was covered by a broad, shallow sea. The sea stretched from Colorado to Kansas and from the Gulf of Mexico to the Arctic Basin. If we look at the fossils, we see that they're distinctly marine. they indicate that the climate was much warmer than it is today. If we go to a place like Greenland, we find fossil alligators. And unless an alligator had fur, the climates must have been much warmer than they are today.
Fossils in the rocks tell of a place in sharp contrast with eastern Colorado's near-desert environment today. 100 million years ago, dinosaurs roamed here in what must have been a lush and tropical world. At the National Center for Atmospheric Research, Eric Barron uses a computer model to find out what might have caused such warmth in Earth's past. The position of the continents is adjusted to the time of the dinosaurs, and other climate factors are added to create an ancient Earth. Barron knows what it was like then. He must find out why.
The Cretaceous geography stored in this computer is clearly dramatically different than the present-day geography. We see, for instance, Australia attached to Antarctica, India in the southern hemisphere, and the evidence for flooding, for instance, here in North America.
His primary clue came from a new understanding of the planet's moving crust, from plate tectonics. Scientists have discovered that the Earth's surface is cracked and broken. In the middle of the oceans is an undersea mountain range where a fiery drama begins the creation of Earth's crust. Hot rock from the interior rises and spreads the sea floor to each side. The result over time is the movement of Earth's continents across the globe.
It's hard to imagine a more dramatic change in the surface of the Earth than what we see here. What is so incredible is that when we plug in this dramatic change in Cretaceous geography into a climate model, we achieve only 1/3 of the warming necessary to explain Cretaceous climates.
What caused most of the warming? At the sites where seafloor is created, explorers in deep-diving submersibles have found towering vents that spew gas and carbon dioxide into the ocean. Gases from the vents eventually escape to become part of the atmosphere. Elsewhere, seafloor is recycled back into the Earth along the world's deep ocean trenches. As the seafloor sinks into the Earth's interior, it melts. Carbon, locked in the Earth's interior for millions of years, rises to the surface and explodes in volcanic violence, once again enriching the atmosphere. By increasing the amount of carbon dioxide in his model, Barron can now account for the extreme warmth of the Cretaceous period. If the model is accurate, the rocks of eastern Colorado should reveal widespread evidence of volcanic activity.
Within these same Cretaceous rocks, we find the evidence for increased volcanism that would have led to increased carbon dioxide levels during the Cretaceous. Each one of these yellow layers represents the rain of ash from a volcanic eruption. As you can see, there are multiple layers. All around the globe, we find similar evidence for substantially increased volcanic activity during the Cretaceous. We discovered that the locations of continents and the flooding of the continents is only part of the story of explaining the Cretaceous warmth. A combination of all of the data and the results from climate models strongly suggest that a CO2 greenhouse effect may have played a major role in explaining the extreme warmth of the Cretaceous. This has probably happened repeatedly in the past. If it's happened in the past, it can happen again.
Now, scientists have added a new chapter to the carbon dioxide story. Pat Zimmerman is an atmospheric chemist. He now studies termites. In the wild, their populations remain in check, but Zimmerman believes the accelerated clearing of rainforests and grasslands may lead to a population explosion that could well influence world climate. There already may be as many as 3/4 of a ton of termites for every human being on Earth.
We think that global termite populations could be increasing. An area of tropical forest roughly the size of Connecticut is cleared each year. And when it's cleared, the ecosystem is greatly simplified. The whole decomposer chain is removed, predators are removed, and that allows termite populations to really explode.
Creatures of antiquity, termites have inhabited the earth for 100 million years. Long studied for their complex social structure, Zimmerman is now monitoring termites for methane, one of a number of warming gases like carbon dioxide. Methane has doubled over the past 150 years, and scientists are concerned about its long-range impact. To measure the amount of methane a termite can produce, the insects are placed in a jar together with a piece of wood. Each jar is attached to an instrument that will analyze how much wood is converted to methane. The primary food of termites is cellulose, found in plants and trees. Few animals can digest it, but termites have evolved one of the most efficient symbiotic relationships in nature. Buried deep in their digestive system is a swarm of microbes that secretes an enzyme to reduce cellulose to sugar. The sugar is then absorbed by the termites. A byproduct of this chemical transformation is methane.
Although this experiment seems pretty simple, nobody had ever done it before. People had realized that termites could emit methane as long as 50 years ago, but nobody had the capability to be able to quantitate the emission rate, and nobody realized that there were enough termites in the world so that that emission could potentially affect the chemistry of the Earth's atmosphere.
The results of Zimmerman's research are intriguing, but evidence also suggests that methane is on the rise from other sources, like swamps and cattle in the increasing cultivation of rice. But methane is only one of the greenhouse gases that now may influence Earth's climate. If these gases continue to increase, they could double the warming effect of carbon dioxide early in the next century, faster and much more alarming than previously thought.
Although this research is in its initial stages and it's still somewhat controversial, there's no question that our Earth and its climate would be completely different if it weren't for the activities of biological sources. Our Earth is a delicate balance between our atmosphere and our biosphere. The emissions from termites illustrate how a single organism has the potential to affect our climate.
Sometime in the 1990s, climate scientists expect to have conclusive proof whether the current warming trend is larger than the normal fluctuations we observe in climate. Climatologist Stephen Schneider.
We in the climate sciences face a big challenge. When are we going to have a global understanding of the climate system, how it will change, and how it will impact upon people and the rest of the planet Earth? The trouble is, we know that we have greenhouse gases increasing. We know that they can have a global effect. It's not new to think that there could be environmental problems. They go back decades. In fact, they go back centuries. The London smogs are a good example, but they were local. Acid rain is another well-known example, but it tends to be regional. What makes the greenhouse effect both unique, interesting, and admittedly disturbing is that it's both global and potentially long-lasting. We have our climate models. They give us a crystal ball, if you will, but they're not perfect. The crystal ball is dirty. And the tough question for us to ask is, how long do we clean the glass before we act on what we think we see inside?
For the first time, man may play an ominous role in the future climate of planet Earth. Although climate changes seem inevitable and the processes that determine it are still not understood, the human species is now a major player in the drama. Today, new tools and technology help scientists assemble the pieces of the climate puzzle. We have now begun to understand the factors that influence the climate of planet Earth. We have uncovered the record of a spectacular past, revealed in Earth's rock, its oceans, the ice and air, and even its life. We have seen devastating ice ages transform the Earth, and tropical climates in places now frigid. We have journeyed into space and found clues to our future. Could Earth become a world of fire or a world of ice? A new frontier of exploration has uncovered an Earth that has changed in the past and will change in the future. How much and when are the questions that remain in the perplexing puzzle of the climate of planet Earth.